Hey everybody, let's talk about power flow. And remember from circuit theory, the formula for the flow of power into or out of some lumped impedance, or which could be some combination of resistors and capacitors, would manifest as an impedance, was defined. The time average power was defined as the voltage multiplied by the conjugate of the current. And there's a pretty straightforward proof for why this has to be the case. But in the general sense of the phasor domain, this is the time average flow of power into a device. Now, in the world of transmission line theory, the same basic idea applies, only now instead of flow into some lumped impedance, it'll represent the flow of power down the transmission line. And in particular, this thing could either be positive or negative, where positive would represent a flow of power to the right down a transmission line. And if this thing is negative, you get a flow of power going in the opposite direction, down towards the left. So what we're going to do is look at the special case of here's some transmission line. And at the end of that line, there is some load impedance. So that's a Z sub L, if you can see that. You can read that. And so there is going to be some energy traveling to the right, striking the load. And as we learned that in the previous lectures, there will also be a reflected wave going back towards the left. So what we care about is what is the flow of power, and how is power determined by the superposition of these two waves here? So remember, the general expression for the voltage down this line was the following: V naught plus the forward amplitude times e to the minus j beta z plus gamma e to the plus j beta z, like so. Okay, so that's the general expression for the voltage along a transmission line when there's a forward and a reflected wave inside the line. Now, given this voltage, there was also a current that we derived, which looked like the following: V naught plus over Z naught times e to the minus j beta z minus gamma e to the plus j beta z. So all we need to do is take these two little terms here, these two guys, we're just going to plug them into this expression over here and just see what happens. So first things first, we need to take the conjugate of this whole thing, right? So I conjugate is going to be the following. I'm going to get V naught plus over Z naught. That whole thing is going to be conjugated times the conjugate of this thing here. So if I were to put a little conjugate here, it actually just kind of distributes to all of the terms. So what I'm going to get is e to the plus j beta z minus gamma conjugate times e to the minus j beta z. Okay, so this here represents I conjugate. Now in particular, this little conjugate is also going to, this conjugate here is going to distribute across these two terms. So what I'm going to get is just a little note here. I'm going to have a V naught plus conjugate, but Z naught, remember that for a lossless line, so we're going to make the lossless assumption, which means this may not generally apply to the fully lossy case, but Z naught was the square root of L prime over C prime. And that's a purely real valued quantity. So if I were to do the conjugate of that, nothing will change. So that conjugate is only going to distribute to the top term, and it won't do anything to change the bottom term. So we're going to get essentially we've already got this here. So we'll just write the conjugate here, and then nothing will happen. So let's just multiply these two terms over here real quick. So I'll have a VZ times I conjugate of Z. It's going to be the following. In fact, I'm going to move it down a line because it's going to be a pretty large term here. So V of Z times I conjugate, like that. I'm going to get, first off, these two terms are going to multiply together. So V naught plus times V naught plus conjugate divided by Z naught. And then I'm going to get this thing here, e to the minus j beta z plus gamma e to the plus j beta z. And this thing over here is going to multiply. I'll get e to the plus j beta z minus gamma conjugate e to the minus j beta z. And then eventually we'll take 1/2 times the real part of that to finish off our expression. But this little guy here is kind of a monster, so we need to simplify it first before we finish the rest of our operations here. So first things first, that's going to simplify. This little guy here is, by definition, the magnitude of v naught squared. And that's just because if I have x conjugate, that will always give me the magnitude of x squared. Okay, so that will simplify pretty well. And again, the conjugate on the z naught here won't change anything because we're doing the lossless case. Although if it were lossy, you could just hypothetically include a conjugate here. But generally speaking, we're not going to care so much about that. And then we got to distribute all of these terms here. Okay, so remember our first, outer, inner, last. So first, outer, inner, and then last again. So let's write this out. I'm going to get equals magnitude of v naught plus squared over z naught. So these guys here, you notice these multiply together to just give you 1. And then this guy here is going to be minus gamma conjugate. And so I have minus in the exponent, or the exponent, will give me a -2. And then the inner plus gamma e to the plus 2j beta z. Sorry, I'm overlapping my green a little, but you should be able to see that still. And then these guys over here, I have gamma times gamma conjugate will be the magnitude, and then these two guys kind of annihilate each other. So I get minus magnitude of gamma squared. Okay, so this looks a little worse than it is because these two terms here have something of the following form. And look at this. You basically have an x here and an x conjugate there. So negative conjugate plus x. You see? So conjugate minus regular plus. So if I have anything of the form x minus x conjugate, what I will get is 2j times the imaginary component of x. Okay? So keep that in mind. I'm just going to leave that as x. So what we'll have is essentially 2j. Actually, pardon me, there should be a minus sign on this. Is that correct? No. That's plus. So I'll have a 2j times the imaginary component of this, gamma e to the 2j beta z thing here. Okay. So the important thing though is this j here, which we're going to throw it away because at the end of the day, I need to take the real part of all this. So you look at this, this is real, that's real, that's real. This sum here is going to be imaginary. So when I take the real part of it, this thing is just going to essentially disappear. So in short, time averaged power is going to be 1/2 times the real part of VI conjugate. So this is VI conjugate right here. If I take the real part of it, this thing is going to disappear. So all I'm left with is going to be magnitude of V naught plus squared divided by 2 times characteristic impedance. I'm going to get 1 minus magnitude of gamma squared. So it simplified out pretty well. It looked a little worse than it was. Just remember, these came together to create a purely imaginary thing, and then when I took the real part of it back here, that just threw it away at the end of the day. So you notice that's a nice, pretty straightforward expression, because if I ignore this, this would be the general expression for the flow of power in some wave. Right? So there's some voltage and some current traveling to the right on a transmission line. If I ignore this bit here, that would just represent the power flow. And because it's positive, it's going to the right. And then you see that I'm just subtracting this guy here. So there's some reflected wave here with a different amplitude. And it's less than 1, so it's always going to be less power than this guy. So at the end of the day, the net flow of power down a transmission line is just the flow of power to the right minus the flow of power to the left, which is nice and intuitive and satisfying.